to the Human Factors and Ergonomics Hub, a series of educational podcasts that showcase the connection between human capabilities and good work design, brought to you by the Human Factors and Ergonomics Society of Australia. Hi, I'm Sharon Todd, a certified professional ergonomist, and I'm chatting with Professor Paul Salmon about systems thinking. Paul Salmon is a professor in Human Factors and is the creator and director of the Centre for Human Factors and Sociotechnical Systems at the University of the Sunshine Coast. Paul has almost 20 years' experience in applied human factors research in areas such as road and rail safety, aviation, defence, sports and outdoor recreation, healthcare, work safety and cybersecurity. He has undertaken extensive research in the understanding and optimising human team, organisational and system performance through the application of human factors theory and work methods.
So, Paul, you are a strong advocate for systems thinking in human factors, and I'm wondering if you could tell me what you mean by systems thinking.
Yeah, sure. I think systems thinking is really a way of thinking about the world that lets us understand why people, technologies, organisations, even societies behave as they do, and also lets us kind of understand where best we can intervene to enhance behaviour and outcomes. Instead of kind of thinking deterministically about things and trying to reduce a complex system down to its part and then kind of optimize the part, stick it back together and hope it behaves better again. It's really about looking at the overall system, all of its different parts, how they all interact and what behavior arises from that. And I think it's important to note that human factors and ergonomics is really a systems science. We are concerned with systems, how the different parts interact and how we can optimise human health and well-being by optimising systems, really.
Okay, so when we're talking systems, we also talk about system failure. So why do systems fail?
Oh, that's a really good question. I think if we start to look at what we mean by systems failure, so maybe something like road safety is a good example. Any time in Australia, when somebody is harmed on our roads, we can say that the Australian road transport system is failing, I guess. And so we can say really the Australian road transport system is failing because it kills between 1,100 and 1,200 people a year. And then if we look at why does the road transport system fail? Why do systems fail? And we use a systems thinking lens, really we can start to see that there are a number of conditions within the system, a number of factors, a number of variables, whatever you want to call them, that interact and create the failure. So, with road transport, again, as the example, we can say that there are aspects of road user behaviour, the road environment, the vehicles that they're using, but also we can look more broadly at the system and say there are things to do with road rules and regulations, design guidelines, driver training and education, even societal issues such as things like addiction, social media and so on and so forth. So it's really systems fail basically because of the way different things across the system interact and create emergent properties. And it's really when we lose control of those interactions and those emergent properties that systems start to fail, I think.
I've actually heard you speak and talk about a generic causal network that frequently appears in incidents regardless of domain. And I'm wondering what that actually is and why does it appear in every domain? So
we did a piece of work where we've obviously done lots of analyses of systems failure in different areas, so ranging from road transport to outdoor recreation, aviation, rail, and so on and so forth. And we started to question, when systems fail, are the causes, if you like, similar across domains, regardless of whether it's road transport, rail, aviation, sport and outdoor recreation, and so on. And so we did a great big meta-analysis of previous, what we call aximap analyses, which is basically an accident analysis technique. And we looked at the different causes across multiple domains, and we found that there was a kind of a common or generic causal network. So what we mean by that is there are certain types of things that happen in complex systems that create accidents or adverse events, and they're quite similar across these domains. So if I kind of remember back to the analysis, there are things like if we think about a system hierarchy and things at the high levels of the system, there's things like policy and procedures, issues with policy and procedures, risk assessment and management, standards, policy and regulations, government failing to act, planning and preparation, personnel management, recruitment. So there are these kind of very similar conditions that we see in systems failures, and they appear in domains regardless of whether it's road transport, sport, outdoor recreation. So that was quite an eye-opening analysis. It tells us that we can really learn from the analyses that people have done in one domain, and we can transfer those learnings across domains, which is really interesting.
So would that mean that enables you to look for those factors in other matters? So every time you approach another analysis of another system, you would specifically look at those categories or contributing factors?
Yes, it's helped us develop methodologies that will support that. And so we can really start to say that, if you're doing an investigation in a certain area, you should look for these kind of issues. And obviously we don't want to bias analyses and things like that, but it does give analysts a guide about what they could look for, what they can check off, basically.
So really that says that there's usually more than one factor involved in the system failure.
Oh, absolutely. I mean, every single analysis we've ever done, and there would be hundreds now, shows that there's always multiple contributing factors involved. And the interesting thing there is that's the case whether the incident is very minor versus whether it's a catastrophic incident that, kills tens, hundreds of people. And a good example there is we have a system called Uploads, which is an incident reporting and learning system for the Australian outdoor education sector. So when they take school kids on camps and things like that, and we find a similar causal network in incidents that are very minor. So think kids getting blisters on a hike. We find similar causal networks in those instances versus, very severe injury incidents where somebody breaks something and has to go to hospital. So, yeah, it's quite interesting. There's always multiple contributing factors, and there's a kind of generic causal network that we tend to see across incidents.
So this shoots in the foot the root cause analyses that have been done over the years, doesn't it?
Yes, yeah. So, we have been quite critical of root cause analyses, and it's obviously a method that has been useful, but yeah, we find it a little bit too linear, and also that it doesn't consider those interactions between the different contributing factors. It might identify multiple factors, but the way we've seen it being used, it doesn't really consider how they all interact and influence and create new contributing factors and so on.
So where you have multiple multiple things in the system that fail, can these systems thinking methods be used to evaluate these types of controls and in a manner that can be understood by someone that is working in maybe manual handling or slip, trips and falls or something like that?
Yeah, absolutely. And the interesting thing I should point out is it's not always failures. So when I talk about contributing factors, a key thing that our work has shown us over the years is a lot of these factors aren't failures. They're just, people making decisions, taking actions as they should be in their normal day-to-day jobs. And it's just how they interact that actually creates the failure. So that's a really interesting aspect of accident causation, and something that people should think about when they're trying to do these analyses is you're not always looking for failures. You're just looking for interactions across the system. So that's an interesting point. But yeah, so the methods, systems HFE methods are really very suited to kind of helping you try and control these interactions and these emergent properties. And, a good example is Nancy Levison's STAMP methodology, which really lets you build a model of the complex system and show you what controls exist in the system and potentially where you might need new controls or where controls might need strengthening. Another method is the event analysis of systemic teamwork, or EAST, from Neville Stanton's group, and that basically shows you how tasks, agents and information all interact, and then what emergent properties might arise from that. So they're all of these methods that are modeling systems at a scale and then trying to understand interactions are all very useful in how you then try and control safety in a particular domain.
So you've referred to behaviours and you've referred to people doing what they naturally do. So how do we manage people's behaviours?
I guess road safety is another good example of this. We're really trying to move away from saying, to optimize safety and behaviour, we should kind of focus in on the people at the sharp end and make sure they're better trained, or put restrictions on them for their behaviour and so on and so forth. We tend instead to look for leverage points in the system that are typically at the higher levels of the system. So away from the sharp end, there are things like policy, regulations, rules, and that kind of thing. And so it's about, I guess, creating the conditions for safe behaviour. And we have to accept that human behaviour is variable. We're never going to restrict a human and make them all behave in the same way in a particular system. It's more about setting the conditions and then controlling, making sure we have controls when the behaviour gets to an extreme point in terms of it's going to cause a problem, I think.
So we need to analyse what we expect a human to do, don't we?
So I think how we expect a system to behave is a way to put it. So you're trying to understand how all of these different components in the complex system are going to interact and how that then will shape human behaviour. And that's really a really powerful analysis when you do that. And it starts to tell you, well, where do we need to intervene in that system? Where do we need controls? Where do we need technology? Where do we need new rules and regulations?
Okay, I think in the past we've been very quick to blame humans for system failures. So what are your thoughts on human error?
I'm quite critical of human error. I understand that as a concept and a movement, it's been quite useful in kind of safety science and human factors and ergonomics research. I think now it's past its sell-by date. I think a human error lens when we're looking at systems failure or accidents is really, it's ethically, morally inappropriate. It's not particularly useful when you're trying to improve system behaviour. And the simple reason is, if you isolate something down to a human error, there's very few ways you can then improve behaviour and performance afterwards. You can either remove the human out of the system, you can tell them not to make the error again, or you can punish them. And the problem is, by doing that, you're zeroing in on the human and the error that they made, and you're ignoring all of the conditions across the work system that actually created the error in the first place. So, I think for me, it's been useful, but it's no longer appropriate, particularly for the complex systems that we're working in today.
There is a theory that if we automate or take people out, that we will obviously remove that risk. What are your thoughts there?
Another thing we've been highly critical of, and, we're kind of standing on the shoulder giants here. So, Lisanne Bainbridge famously wrote a paper many years ago that talks about the ironies of automation. The problem here is by, replacing a human with an automation, you're actually making the system more complex, more brittle, more prone to failure. And you're just creating more problems. And, there's all the ironies of automation for the listeners is a great paper to read, very simply put, about some of the issues that you'll encounter. So I think, that's a real issue, because currently at the moment, I've been involved in projects where organisations think we're removing a control room operator and we're putting automation in, therefore we're making the system much more reliable and safe. And actually, it's the opposite.
Okay, so we need to evaluate the system and all the contributing factors in the system. So in using systems thinking methods, you've talked about STAMP and EAST. What are some of the others and how do they work? We
published a book recently at the Handbook of System Thinking Methods, and we kind of break it up into different kinds of methods. So there's prospective risk assessment methods. So these are methods that you apply. You basically model a system and you try and forecast risks that are going to emerge, over time. And so that's things like STAMP STPA, the Networked Hazard Analysis and Risk Management System, or NetHarms, the EAST Broken Links approach. So that's where you're kind of trying to predict or forecast risks. We have systems analysis and design methods. So that's, a most popular one there is probably the cognitive work analysis framework. So this is a method where so there's actually 5 phases to that, but you're basically you're developing a model of the system, and then you're really analysing aspects of the system in real depth, in real detail. And that method, you look at decision making, you look at allocation of functions. So who's doing what in the system? Is it humans? Should humans be doing certain tasks? Should technology be doing it? You're looking at strategies analysis, so what are all of the different ways in which a task could be undertaken, and that gives you a sense of the performance variability in a system, and so on and so forth. And the neat thing about cognitive work analysis is it's really a formative method. So, like something like hierarchical task analysis, you're analysing how the system does work, whereas cognitive work analysis, you start to look at, well, here's how the system currently works. Here's how it actually could work if we made some changes. So it starts to move us further down a design path than just a kind of descriptive and analytical path, which is really interesting. The other group of systems HFE methods, of course, are accident analysis methods, so retrospective event analysis methods. And here you have things like AxIMAP, or the accident mapping technique, StampCast, AxiNet. FRAM can be used as well to analyse accidents. So they're basically, when the bad things happen, you then do a really exhaustive analysis of all of the factors across the system that interacted to create the adverse event. And then an interesting and kind of more recent set of methods, particularly if we think about HFE, are what we call computational modelling methods. So these are methods where you develop a model of a system, and then you can simulate the behaviour of that system over time. So an example of some work that we did there. So these are things like system dynamics and agent-based modelling. And we're currently using agent-based modelling to simulate future artificial general intelligence systems and see what risks are going to emerge in those. And we've also used system dynamics, for example, to say, if we have a problem like drink driving, and we have a series of interventions, what is the reduction in crashes and trauma that we'll get with the different interventions? And so you can start to kind of, assess the impact of different interventions within the system. And for HFE, that's particularly important, because a big problem with our discipline, I think, is we're often going into organizations and saying, these are the interventions we think you need to make to either increase efficiencies or enhance safety. And the question always is, well, can you give us any guarantee that they're going to work? And obviously, often we say, well, no, we think it will, because we've done the great human factors analysis and the design, but we really have no idea. So with some of these methods, we can start to get some sense of, how well they're going to work, I think. So, and I think that is really an important area for human factors and ergonomics to kind of look at, how we can give evidence that our interventions are going to actually achieve the benefit that we're supposed to.
Wow, computational modelling. Can you talk about a project where you've used that?
Yeah, sure. So one project that we're using it at the moment, there's two particular methods. I'll talk about a couple of projects. So the first one is system dynamics. And so what we're doing at the minute on a project with that is we're building what we call a digital twin model of the Sunshine Coast Hospital and Health Service. And so what we're doing there is we're basically building essentially a model of the health service, the local health service, where we can start to simulate its behaviour over time and say, hey, look, if you make these different policy interventions, these are the likely effects that you're going to get on things like, patient flow, patient waiting times, and things like that. So they can start to, when they're making decisions around different policy interventions and different changes they want to make to the health system, they can start to have some data around, well, what's that likely to do? How is that likely to unfold over the next 25 years or so? And so that's one project. And with agent-based modelling is a little different. So system dynamics is the kind of broad systems analysis, where agent-based model is looking at, groups of agents within the system and how they behave. And so with that one, we're actually looking at, really kind of future-looking artificial general intelligence systems, particularly a road transport system and an uncrewed aerial vehicle system. And we're basically saying, if we have these really advanced artificial general intelligence systems, what behaviours are going to happen? What are some of the behaviours that might emerge? And the neat thing with agent-based modelling is you build a model of the system and you kind of let it run, and it often behaves in really unexpected ways. And so what we're using that for is to see if there's any, kind of risks to safety, risks to humanity, even existential risks. And that's kind of a really interesting program that we're using at the moment as well.
You would need to understand the job or the task or the system really well to analyse all the agents.
Yeah, that's correct. And so, the reason we kind of started using computational modeling methods is that we think all of our systems HFE methods are really very good at specifying the initial conditions for the models, if you like. So, for example, in the AGI, Artificial General Intelligence project, we've used cognitive work analysis and the event analysis of systemic teamwork and the STAMP method. And we've built models of these future AGI systems. And then we've taken those models and kind of translated them into an agent-based model. So, yeah, the initial systems HFE models give us that, detailed understanding of the system. And then we put kind of those learnings into the ABM model, and then that kind of simulates how those systems might behave. And the problem with, the one big limitation of systems HFE methods like STAMP, like cognitive work analysis, like EAST, is they're static. We're modeling the system at a snapshot or a point in time, and it can't, it's not dynamic, it's not simulating behavior, it's not doing things. Whereas things like system dynamics and agent-based modeling, they're actually simulating behavior of the system. And that's the idea with the digital twin healthcare project, is we're actually building a living, breathing model of the local health service, and it starts to do things and behave, and we can kind of pull different levers and say, well, what is the effect if we pull this lever? What happens if we pull this lever?
So with AI, I'm assuming there hasn't been much systems analysis before we've gone down this path, and the horse has already bolted. How do we rein some of that in?
Yeah, that's a really good question, and you're right. I think, AI, there's been very few people thinking at this kind of systems interactions complexity level. The Centre for AI Safety has started to put out some work around looking at sociotechnical systems and talking about things like STAMP and control structures. So that's great news. But you're right, the horse has bolted. So the project that we're looking at is the next iteration of AI, which is AGI, which is apparently going to be more intelligent than humans. So we're trying to get in early at this point and stop that one ending the world. But we'll see how we go. But I think it was a major. It's not the fault of HFE. I think that we messed up with AI, but I think it gives us some very clear messages that we're not quite so well known in other disciplines as we should be. Like, I really feel that we have a massive contribution to make to AI and AI safety, but I think not enough people in those fields are aware of us and what we do. B, we don't disseminate or communicate our success stories very well. So I think it's a big challenge for our discipline that we need to be more involved in these future advanced technologies, because we really do have a big contribution to make.
Did you say that there is actually a Centre for AI Safety? Where are they?
Yeah.
Where are they? What are they doing?
They're in the US, and they're kind of looking. Basically, there's actually a few groups around. There's also the Future of Life Institute, and they're doing lots of work which is really looking at the risks associated with future advanced AI, but they're also trying to slow these AI development programs down because of the risks that are now emerging. So, really important groups, really critical that they are allowed to do the work, and it's really fantastic to see that they're starting to use some of the systems or explore use of some of the systems HFE methods that we know and use frequently.
So you've indicated that we, in this space, HFE professionals really haven't said enough about what we can do and how we can do it. Is the Centre for AI Safety reaching out, or is there HF involvement in that?
I mean, I don't know the specific composition of the group there, but we're reaching out to them, I think is the way to put it. We're trying to make them aware of the work we're doing, and initial chats to them, they're kind of keen to see what we're doing, and we're keen to help them with what they're doing. But typically not the Centre for AI Safety specifically, but if we think of AI development programs, you typically got a lot of techie people, who's developing the actual AI systems, and I think far less people in disciplines who are thinking big picture about the risks that can emerge from a particular technology. And, I guess it's part of the human condition. We get excited with, something that is really advanced and can do new things, and we kind of push it to see if it can do more things. And sadly, thinking about the risks often comes afterwards. And I think that's kind of what's happened here.
Okay, so really AI would be a complete new podcast on another day, which I'm excited to talk about at some stage. I'm going to come back to systems thinking just generally for a second. And we've talked about emergent risks, we've talked about task interdependencies, and I've heard you talk about feedback loops. And we've talked a little bit about that already. Can you maybe just break down some of those concepts for us a bit further?
Yeah, sure. So feedback loops, basically all complex systems are made up of, interacting feedback loops. And basically, I guess a simple way of putting it is to say a feedback loop is where a change in something or one variable leads to a positive, negative change in another. And the one I always use in kind of presentations is the chickens and the roads kind of feedback loop. So, if you've got the more eggs that are laid by chickens, the more chickens there are, and then the more chickens there are, the more eggs are laid. So that's like a positive or reinforcing feedback loop. But then you can add a negative balancing feedback loop to that, and you can say the more chickens there are, the more road crossings by chickens there will be, and the more poor chickens it will get killed by cars, which then acts to balance or limit the growth of the chicken population. And so basically, all systems are made up of these different interacting feedback loops, and it either, puts a limit to growth or it, increases growth. And so that's a kind of feedback loop. Task interdependencies is just quite simply how tasks in a system are related. So often we find the tasks across the system, they're all really interdependent. And that means, the conduct of one task will influence the conduct of another, or one task might not be able to be started until one's completed, and tasks may be done together and reliant on each other. So it's basically how dependent they are on each other. And it's very similar to Perrow's tight and loose coupling, so how kind of interdependent the tasks are within a system. And I think what you find in most complex systems, or certainly the analysis that we do, is that there's a high degree of interdependency or coupling between certain tasks, and then some are more loosely coupled. And the interesting thing is high interdependency can be really bad in cases. If one task fails, then all of the others are going to fail. But it can also be good in cases. And then similarly, loose coupling or loosely interdependent tasks can be very good in some cases and bad in other cases. So it's really quite complex about which one is the best one to have. And then I think the final one you mentioned was emergent properties. And that's just simply, when we're looking at complex systems and we see that there are components interacting, so it might be people interacting or people and technologies or people and artifacts, it's just the behavior that arises from that interaction. So if I'm interacting with a pilot in a cockpit and we're interacting with technology, what is the emergent property of that interaction, basically? And when we think about risks, we often talk about emergent risks. And so what we're saying here is there are often risks or conditions or across a system, and when they interact, they might create a new emergent risk. And they're really the ones that we find are quite elusive and the ones that get organizations into trouble. Often they know a lot about these other risks, but they haven't really understood that when these two things interact, there'll be a new different risk. And so that's basically how we talk about those.
So this really shows us that risk management is a dynamic process, and the old process of just using a tick and flick checklist that's used quite often in lots of industries just doesn't cut it anymore.
No, absolutely not. And there's the tick and flick doesn't work. The brainstorming session with a few people doesn't work. And really, what our work has kind of showed over the past few years is organizations can have a really good understanding of risks at the sharp end. So, the risk that the pilot is going to press the wrong button or put in the wrong airspeed or wrong control inputs. It's really those other things across the system that they have no handle on. So, for example, the risk that their policy and procedure is going to drive, inappropriate behavior or substandard behavior. The interaction between their risk assessment process and their instant reporting and learning system is going to create a gap in knowledge. It's those kind of risks away from the sharp end, if you like, that people don't seem to have a good handle on and seem to get people into trouble or organizations into trouble.
So this process is about getting all the pieces of the puzzle together and then looking at how those components can change with the interaction of other components, and then understanding what the potential risks look like. And then that's at one end, isn't it? And then the other end is looking at what's actually happened and learning from problems that have arisen and system failure.
Yeah, absolutely. Yeah, it's all about interactions. You're modelling, you're trying to basically get a description or model of the system, and then you're trying to understand what all the interactions are and what the outcomes of those interactions are. And then that will gives you very kind of powerful insight into how a system will behave, why a system behaved in the way it did. And really what we're doing, in whether the analysis is prospective and we're trying to forecast risk, or whether it's after the fact and we're trying to understand why a big accident happened, we're really looking for leverage points. So, the listener, I point the listener to Danella Meadows' work. We're looking for areas in the system where you can make a small change and it will really create dramatic change in behaviour at the kind of sharp end of the system. And really all of these analysis methods are really helping us do that, find those leverage points basically in a system.
Okay, so then reporting of near misses and things like that are extremely important then if you're going to analyse systems.
Yeah, absolutely. Very powerful, very important. And I think, again, with the same line of thinking, and I see this with a lot of incident reporting systems, it's not just getting information like an incident report that says, the wrong medication was delivered to the patient and it's because the nurse made an error. It has to go beyond that and try to understand some of those influences on the nurse's behaviour. What was the workload like? What was the rostering like? Was it busy? What's the procedure for this thing? What's the labelling of the medication? All of these different other factors. It's critical that you get information on those as well. Otherwise, the reporting system isn't particularly useful. And again, a lot of our work at the minute is really developing incident reporting learning systems that are kind of aligned with systems thinking. They do try to get that information about conditions across the system that really created the sharp end behaviour.
So you've talked about systems thinking in complex socio-technical systems. My question is, can we use this, or can we simplify it to use it for something like manual handling?
Yeah, absolutely. Absolutely. And the interesting thing is, basically, this might be kind of a broad brushstroke, but any system, I think, becomes complex when you put humans into it, right? So I think these methods apply to any kind of human factors and ergonomics application area. Manual handling risk, manual handling injuries, musculoskeletal disorders is one area where we've applied the methods, so they work just as well in that area for sure.
So what have you applied and what works?
So we've done the kind of retrospective analysis to look at manual handling injuries or musculoskeletal disorders and try to look at the conditions across a work system that kind of influence that. The more recent work, we had a PhD student, Peter McCormack, who was looking at developing a new method to actually identify hazardous manual task risks. And so we did a whole lot of work looking at existing systems HFE methods, like FRAM, like East Broken Links, like NetHarms, also STAMP STPA. And we said, do they work in this context? And so they did. We did some testing on that. But then we said, what, they probably need a bit of tweaking. And so the way that work ended up is Peter took the kind of principles of STAMP STPA, and then he developed his own kind of method, which is called Hamster, I think, which is an interesting name. I think that's hazardous manual task systems thinking analysis or something like that, assessment maybe. So he developed a whole new method which is used to forecast hazardous manual task risks, basically.
Where do we find that information? Obviously, it's out there somewhere.
Yeah, there's a couple of papers. So one, he did a great big systematic review to say, has systems thinking been applied in this context? So basically your question. And the kind of the conclusion there was not really. And then he did some work to say, well, could it be? And we did some testing the methods, and that said, yes, these methods work. And an output of that study was that, they all work pretty well, I think, but STAMP STPAs seem to work the best. And so then based on that, he did some work with a couple of organisations and he developed his new method. And I think they're published in Safety Science and Ergonomics, I think. But if people send me an email, I can send them the papers through for sure.
In that study, was there anything unusual that came out of that analysis that you wouldn't have found with a chicken flick?
Not the comparison study, because with that we use like a hypothetical scenario. But I think what Peter's work has shown really is that there are all sorts of higher system level conditions that create the risk of musculoskeletal disorders or hazardous manual task injuries, and it's possible to identify them with a structured method, I think, is what he showed. So I think that's the main take home of the message. Basically, current prospective risk assessment methods in this area are very, as I've mentioned, focused in on just the worker and the work context, and there's a whole load of other risks that really need to be considered.
So what are some of the biggest lessons that you've learned in managing system failure and using these tools?
Well, that's a really interesting question. I think there's a number of classic quotes out there about system is perfectly designed to get the results it gets and things like that. But I think the main lessons I've learned really is that any incident, whether it's really minor or catastrophic, will have multiple contributing factors, and often that network of contributing factors is quite similar. I think human error really is not a cause of anything. It's a consequence of conditions across a system. So I think, let's forget human error. Sidney Decker would always say, to understand accident causation, we have to go up and out into the broader system rather than down and in into the sharp end and people there. And then really, trying to fix just a part of a system without considering all of the interactions and the other conditions across the system really isn't going to, give you any benefit whatsoever. One of the key things we've learned is it's really about looking for leverage points, and you're really trying to optimize systems rather than the parts of the system. I think those are some of the big lessons. Plus the generic causal network, I think that was an eye-opener for me. I think that was really interesting.
What are some of the important future applications of systems thinking?
I mean, we've talked about AGI, so I think for the future, the interesting thing, I think there's lots of really, advanced technologies coming our way. And, the more advanced these technologies get, the more complex they become, and the more dependent we are on them as a society, the kind of bigger the problems are if they're not well designed. So I think Human Factors and Ergonomics really has a critical role in making sure that all of these fancy advanced technologies aren't going to wipe out humanity. And I say that, it sounds tongue-in-cheek, but I'm pretty serious about that. If we don't get artificial general intelligence right, it really could replace humans. It really could lead to human extinction. So I think it's really critical that HFE is involved in the design, implementation, operation of all of these advanced technologies. And I think if we're not, there's not only going to be catastrophic outcomes, but we're failing as a discipline. It's really what we're here for. We're here to, understand complex systems, optimize the design, make sure we optimize human health and well-being. So it's not like we shouldn't be having a role in these things. It's just that we're not having it as big a role as we should have, I think.
So how are we going to gain leverage on that?
I think we have to, as a discipline, we have to learn to work better with other disciplines. We're not going to solve the problems of artificial general intelligence by human factors people talking to human factors people. We have to be involved in the development programs. We have to be working with tech developers, all of that business. So we have to work better with other disciplines. And to do that, we have to let other disciplines know what we do. We have to communicate our success stories. And we do have them, and we have lots of them. We just don't communicate them very well. And I think we have to continually as well evolve our own methods and theories. Artificial general intelligence is a good case in point. Do we actually have, we're called human factors and ergonomics. Do we have theories and methods that can cope with a machine that has intelligence and consciousness? Do we simply take methods that we've applied to humans to measure that, to assess situation awareness in a non-human agent, or do we need a whole new suite of methods? So I think we also have to be continually evolving our own kind of theories and methods as well.
Surely we would also need to engage government, because I think there's a lack of understanding there.
Absolutely, yeah. And, that goes to, pointing out, better communicating what we do, what we know, all of that stuff. I think we definitely have a problem in HFE where we're very good at telling each other what we do and what we're good at, but we're not particularly good at telling other people outside of our discipline what we're good at and what we can do.
Thanks for joining us at the Human Factors and Ergonomics Hub, brought to you by the Human Factors and Ergonomics Society of Australia, where human-centred design really matters. If you like this podcast, make us your favourite in your podcast app. We look forward to chatting with you next time.